Hello, everyone. This is Xiaobing Liu from Oak Ridge National Laboratory. I'm very glad to virtually present our work. The title of this presentation is Performance Analysis of a Membrane-Based Ionic Liquid Desiccant Dehumidifier. So this is the contents of this presentation. It includes the introduction, experimental operators of the proposed dehumidifier, experimental results, and parametric study. The last is the conclusions. First, let's start the introduction part. We know that the global electricity generation is rapidly increasing during the past decades. Two-thirds of it is generated with the fossil fuels. So the consumption of the fossil fuel release huge amounts of greenhouse gas and cause global warming problems. Buildings, as the primary user of electricity, consume about 75% of total electricity, of which 40 to 70% is consumed for summer loads, including heating, cooling, and air conditioning. So this figure shows a traditional schematic of the air handling unit. So the air is usually need to be coated with treated water, and it's also dehumidified using low temperature condensation below its dew point. And the overall coated air needs to be reheated to comfortable temperature. So this is the principle of the traditional vapor compression system. In this process, a large energy needed to be consumed. 20 to 40% is consumed for air dehumidification. But large part of this energy is actually wasted due to the overall cooling and the reheating. So the energy saving for air dehumidification is very important, and it can largely reduce the fossil energy consumption. People propose many types of alternatives. Most of them are the non-vapor compression HVAC systems. One of the most promising technologies is liquid desiccant dehumidification. So different from the low temperature condensation, the air dehumidification by using liquid desiccant can be achieved at a room temperature. The air moisture in the air can be removed by the pressure difference of water vapor between the air and the desiccant solution. The liquid desiccant dehumidifier can be divided by the packed type, membrane type, and the folding film type. The desiccant need to be regenerated after it is used for dehumidifying the air. And the regeneration can be driven by low-grade renewable energy, such as by solar energy, by geothermal energy, and industrial waste heat. Actually, the liquid desiccant-based air conditioning system has the potential to reduce 1 quart annual primary energy in the US. However, there are some drawbacks of the existing liquid desiccant technology, which limit the practical application of liquid desiccant technology. For example, the liquid carryover from the packed type dehumidifier, the metal corrosion by the salt desiccant, which is commonly used now. And when used the porous memory-based dehumidifier, the blocking and the folding is also a big problem. So to solve this problem, we proposed a novel liquid desiccant dehumidifier, which using the non-porous membranes with the tubular design, and also using the Ionic liquid desiccant. We developed the benchtop prototype and also conducted the dehumidification test. This figure shows the benchtop prototype of the dehumidifier. So the left two figures shows the SEM images of the memories. The figure below is the non-porous memory we used. So compared with the porous memory, there's no air gap inside of the membrane, non-porous membrane, and also the surface of the non-porous membrane is also smooth. So, so it can avoid the blocking and the contamination by using these nonporous membranes. And the membranes also adopt the multiple tubular design to minimize the uneven distribution of desiccant solution and leakage compared to the flat sheet membranes. We also adopt the cross-counter flow to enhance the convection and use the mesh reinforcement for the membranes to improve the strength of the membrane. In this study, we used the Ionic liquid desiccant. This Ionic liquid desiccant is a novel type of acetate with a mass fraction of 70%. There are many types, many advantages of this type of Ionic liquid desiccant. For example, there's no crystallization problem, and it has a very low vapor pressure at mass fraction of 70%, and there's no corrosion to the metals, and the regeneration temperature is also low, which can use the low temperature heat. So this characteristics make it's a very good substitute to the traditional salt desiccant solution. This is the schematic diagram of the proposed experimental operators. The right side is the proposed dehumidifier. The left side is the Ionic liquid desiccant set. The Ionic liquid desiccant from the concentrated solution is pumped to the dehumidifier for the air dehumidification, and then it pump out to the diluted solution tank. So using this experimental apparatus, the air dehumidification and the air and Ionic liquid desiccant regeneration can be characteristic tested. The following variables can be controlled during the test. They are the air flow rate, humidity, and temperature, and also the Ionic liquid desiccant flow rate, concentration, and temperature. This figure shows the photo of the experimental operators built in at ORNL. This is the air and the dehumidifier site, and this is the Ionic liquid desiccant site. This table shows the specifications of the measuring instruments during the test. The measured parameters include the temperature, flow rate, density of the Ionic liquid desiccant, and it also includes the flow rate, relative humidity, and the temperature of the air. To evaluate the dehumidification performance of the dehumidifier, so we use the two performance index. The one is the absolute moisture removal rate. So it is the amount of the water vapor removed from the air per unit time. Another index is the dehumidification effectiveness. So it is the ratio between the actual mass transfer rate to the maximum possible mass transfer rate in the dehumidifier. It can be calculated by using the equivalent humidity of the inlet Ionic liquid desiccant. We conducted an experimental case to test the dehumidification performance. In this case, the air condition is the typical summer humidity air condition, and the temperature of Ionic liquid desiccant is around 20 degrees C. So this figure shows the measured data of the air and the Ionic liquid desiccant. So we can find that the test results are very stable during the test. And the measured performance shows that the moisture removal rate is around 124 grams per hour, and the effectiveness of this test is around 9.4%. To comprehensively understand the performance of the dehumidifier, we conducted a parametric study under two different conditions. The first condition is when the inlet Ionic liquid desiccant at a low temperature around 21 degrees C. So first we studied the impact of the air flow rate by conducting these three tests. with the varied air flow rate from 34 to 112 cubic meter per hour. The other variables of the air and the ionic desiccant were kept at constant and almost the same between these three tests. So this is the measured performance at different air flow rates. So we can find that the moisture removal rates increased from 75 to 180 grams per hour, while the effectiveness decreased from 22.7% to 9.3%. The reason is that when the air flow faster through the membranes, the contact time between the air and the membrane become shorter, and it causes the decrease of the effectiveness. We also studied the impact of the liquid desiccant flow rate. In these three tests, the flow rate of the liquid desiccant varied from 0.4 to 2.1 gram per second. This is the measured performance. So we can easily find that both the moisture removal rate and the dehumidification effectiveness increase by increasing the solution flow rate. The reason is that when the solution flow rate increase, the water vapor pressure inside of the solution inside of the dehumidifier can keep low. So it is beneficial to the dehumidification performance. We also conducted the parametric study under another inlet ionic liquid desiccant temperature. It is at a high temperature, around 34 degrees C. So this is the condition without the pre-cooling for the ionic liquid desiccant. We studied the impact of the air flow rate. During these three tests, the air flow rate varies from 18 to 92 cubic meter per hour. And this is the measured performance at different air flow rates. So we found that the moisture removal rates increased from 15 to 55 gram per hour, while the effectiveness doesn't show the linear relationship with the air flow rate. We can also find that the dehumidification performance at low ionic liquid desiccant temperature compared to the performance at low ionic liquid desiccant temperature, the performance at high ionic liquid desiccant temperature are much lower. To conclude this work, the experimental results demonstrate the dehumidification performance of the proposed novel dehumidifier, which is using the nonporous membrane and the ionic liquid desiccant. We found that a higher absolute moisture removal rate can be obtained by increasing the air flow rate and ionic liquid desiccant flow rate. And the dehumidification performance deteriorates with the increase of the ionic liquid desiccant temperature. And in this study, the maximum absolute moisture removal rate achieved is 180 grams per hour, and the maximum effective achieved is around 12.7%. To improve the performance of the dehumidifier, the optimal design of the dehumidifier is to be conducted during the future work. And the ionic liquid desiccant regeneration by utilizing the low-grade or renewable heat sources is also needed to be conducted in the future. That's all. Thank you.